This is like my 6th time recording this because Premiere likes to crash and the last one just didn't save, so I digress. Anyways, tension, whether it's between people or objects, it's not really fun to deal with. I'm going to focus more on the objects because I'm not really a fan of social sciences. It's always good to start with a definition. Define tension.
The state of being stretched tight.
Now that's a garbage definition, so I made my own. I define tension as the force exerted by an object onto the string suspending it. Of course, you can have a string pulling something sideways, but let's take a look at a single string holding up a block of mass m. We know that the block has a weight force down, which I'm going to call W, equal to mass times gravity. And I will be calling gravity 10. I'm rounding it up. And if you don't like it, well, you're not making this, so too bad. Anyways, Newton's third law states that every force must have an equal and opposite force. In this case, the opposite force is the tension, which is equal to negative mg. Since I'm calling down positive, up has to be negative. It's just the opposite sign. You get the idea. So let's be realistic here. If you're given a tension problem, you're not going to get something that easy. So let's look at something you might actually see. For your first introduction to tension, you're probably given something looking like this, where you have two strings holding up a block of mass m at equal angles. There's a proof I could do that shows why I'm able to say what I'm about to, but I'll get to that later in the video because it requires a little more advanced math. But for now, we're going to say that each string receives half of the weight force. So in other words, if we take this system, this two-string system, and we break it up into two separate pictures, we can say that each y value is equal to 1/2 the weight force, or 1/2 times mg. So once we've done that, we can now see that y1 equals y2. And I'm going to do something very simple here. Our angles are equal, so we have one equal angle. Both have right angles, two equal angles. y1 equals y2, that's an equal side. So we have an equal side and two equal angles. That proves that both these triangles are equal. Now, why did I do that? That proves that T1 also equals T2. So we really only have to solve one system to solve for the whole thing. So we can just redraw as one triangle now. If we're looking to find the hypotenuse and we're given an angle on the opposite side, we're going to use sine because sine is the opposite over hypotenuse. So sine of theta equals y over t. And when you multiply over t and then divide by sine theta, you get t equals y over sine theta. Now let's substitute some numbers in for this. So let's say we have a mass of 2 kilograms and a theta, or an angle of, let's do 30 degrees because it's easy. Sine of 30 degrees, 1/2 mass times gravity, so 1/2 times 2 times 10, in other words, 10, over the tension, t. That's what we're solving for. Do our math, t equals 10 over sine of 30. Sine of 30 I know is 1/2. Tension equals 20 newtons because 10 divided by 1/2 is 20. And because we said T1 equals T2, both of our tensions are 20 newtons. So you can see that one is actually very simple. Another tension system you might see very early on is one where you have two strings again, but one is horizontal and the other is at an angle. It looks harder than it is. And there's a reason it's easy, and I'm going to go through that. So we're looking to find the tension on both the horizontal and the angled string. Now, how do we do that? Well, it's actually fairly simple if you see where it all comes from. So let's start, I'm going to start at least by drawing a vertical line here. And again, a proof that I'll go through later, this vertical line is equal to mg. Now, let's take another line, draw it from the top of mg over to the end of T1. If you take everything else away, you'll notice that this is a system of two sets of parallel lines. Our first set is the horizontal ones, and the second set, the angled ones. And we're given angle theta between one of the angles and one of the horizontals. And we need to find alpha, which happens to be this one. And there's a reason we're going to find that. Since these are all parallel, one line intersecting two parallel lines, well, these two angles are equal. Theta is equal to angle 2. And shifting our focus to this system, we can also say that angle 2 is equal to angle alpha. And since angle 2 is equal to angle theta, therefore angle theta equals angle alpha. So, looking back at our tension system, we just proved that angle alpha can now be rewritten as angle theta because they are equal. So now, again, we have two equal angles and an equal side. So therefore, these are equal triangles, but this isn't going to prove what you think, or at least it's not going to prove what it did before. Let's take this and let's break this apart. Since we know these triangles are equal, we can do something. We can take this left triangle with T1 and rotate it, and you can notice that the left triangle is actually just a 180-degree rotation of the right triangle. So we can now say that T1 is just the horizontal component of that one triangle. So we get T2 on the hypotenuse, T1 on the horizontal component, and our weight force mg on the vertical component. So let's start with T1. We're given an angle and the opposite side, and we need to find the adjacent side. So we're going to use tangent, because tangent of an angle, so tangent of theta, is equal to the opposite side over the adjacent side. In other words, mg over T1. Multiply and divide, T1 equals mg over tan theta. Now looking at T2, again, opposite side, looking to find the hypotenuse. We did this in the last one, so I'm just going to skip it. T2 equals mg over sine theta. So what's this look like with numbers? Well, let's say our mass is 3 kilograms this time, and let's say our angle is 45 degrees. So T1 equals mg over tangent of 45. Tangent of 45 is 1, so T1 is a 30 Newton tension. T2 equals 30 over sine theta, so sine of 45. And when you simplify that, T2 is about 42.43 newtons. This system is also a little special, but I'm going to get to that later. Now, this is where the easy stuff ends. You'll likely see this in a college physics course where you have two strings, again, holding up a block of mass m, but this time the strings are at different angles. So I'm going to enable them alpha and theta for T1 and T2 respectively, and it's holding up a block of mass m. All right, in order to do this, we need to build a system of equations. And in order to show you where that system comes from, I'm going to make a table of values. It's probably good to know how to do this as well. So I am going to walk you through it. So make a 3-row, 2-column table, and you want your columns to be a bit thick. Label the left column X, the right column Y. First row T1, second row T2, and final row total. Now, let's take a look at this. We know that the total force in the X direction, so the total horizontal force, must equal 0 because this block isn't going anywhere. Whatever's suspended isn't moving. It's just sitting stationary, being held up. So our force in the horizontal direction is 0 newtons. Now our force in the Y direction is equal to mass times gravity, and that's because of Newton's third law. The weight force down has to have an equal and opposite force up, so the total Y has to equal mg. Again, we can break this up into two triangles. If we're going to find the X component of this first triangle, we're going to use cosine, because cosine is the adjacent side over the hypotenuse. So cosine of alpha equals x1 over t1, multiplied by t1, and t1 cosine alpha equals x1. So in the X column, t1 row, we're going to write T1 cosine of alpha, because that equals the X component for that string. And the same goes for T2. T2 cosine theta equals X2. Now the Y component is also pretty simple. Opposite over hypotenuse, that's sine, multiply over the tension. T1 sine of alpha is y1, T2 sine of theta is y2. Now, we have components and we have totals. So let's build the system of equations. Let's start with the X. The sum of all the X components must equal to 0. Well, that means that one of them must be negated. I'm going to negate the second one. So T1 cosine alpha minus T2 cosine theta equals 0. And we also know that the sum of all the Y components must equal the weight force. So T1 sine of alpha plus T2 sine of theta equals mg. Now I'm not going to plug any numbers in yet because I'm going to do something very specific that will help us later on. But we'll get to that. So first, to solve a system like this, it's best to use substitution. We're going to solve for T1 in the first equation. So we get T1 cosine alpha, add T2 cosine theta to the other side. So T1 cosine alpha equals T2 cosine theta. Divide over the cosine alpha and you get T1 equals T2 cos theta over cos alpha. Now those don't cancel out because they are different angles. Keep that in mind. So now we're going to substitute that back into our Y equation. So instead of T1 sine alpha, we have T2 cosine theta over cosine alpha times sine theta plus T2 sine theta. You see how that substitution worked? I'm going to do something very important here. Notice how each term has a T2. I'm going to factor that T2 out. So now we get T2 times cosine theta over cosine alpha times sine alpha. And I'm going to put that sine alpha in the numerator, if you don't mind. And then we're going to get plus sine theta equals mg. Now, this is where the fun stuff comes in. That cosine theta sine alpha over cosine alpha can be simplified to cosine theta times tangent alpha. So now we have T2 times cos theta tan alpha plus sine theta. We just divide that over and we get T2 equals mg over cosine theta tangent alpha plus sine theta. Now, this equation is how you can find the tension in any system. This equation right here. Remove the 2. I'm going to redefine our angles. Our theta is our adjacent angle and our alpha is our opposite angle. So let's look at our picture again to see what I mean. Notice how we're solving for T2. Theta is the angle adjacent to T2, and alpha is the angle opposite to T2. That's where that comes from. So you can rewrite this as tension equals the weight force divided by the cosine of the adjacent angle times the tangent of the opposite angle plus the sine of the adjacent angle. Now, I know that's a little confusing, so I'm going to show you this in action. You could solve the system normally through substitution, but personally, I like this equation better. I'm totally not biased because I made it up. Let's say alpha is 42 degrees and theta is 61. Just two random angles. Using this, let's find T2. So T2 we defined as cosine of the adjacent angle, so cosine of theta, 61, times tangent of the opposite angle, tangent of alpha, so tan 42, plus sine of the adjacent angle, sine theta, or sine 61. And that's all under the weight force, mg. Oh yeah, I forgot to define my weight. Let's use m of 4 kilograms. We end up with 40 over cosine 61, tangent 42, plus sine of 61. And when you plug that massive garbage into your calculator, you will get T2 is about 30.51 newtons. Well, that's great and all, but how do you find T1? Reverse the angles. Remember how I said it was adjacent and opposite? There's a reason I defined it like that. T1 equals the weight force, 40, divided by cosine of the adjacent angle. Now we're on the other side, so the adjacent angle is alpha. So cosine of 42 times tangent of the opposite angle, 61, plus sine of the adjacent angle, 42. And you will get a T1 of about 19.9 newtons. And there you go. All of tension simplified into a single equation. Now, I'm not quite done yet. I'm going to take this equation, I'm going to go back to the previous systems to do those proofs that I said I would get to later. So let's start with a system with equal angles. Remember how I said that the tension is equal to 1/2 the weight force over sine of the angle. I can prove why that is now. And I can also prove why each string gets half the weight force. Tension equals mg over, let's just use tension 1. So cosine of the adjacent angle, theta, tangent of the opposite angle, theta, plus sine of the adjacent angle, theta. Oh hey, they're all theta. Let's take that denominator and we'll break it up into cosine theta times sine theta over cos theta, because tangent is sine over cosine plus sine theta. Well, look, those two cosines cancel out. So now we have tension equals mg over sine plus sine, which is 2 sine theta. Well, now I can factor that 2 out. T equals 1/2 mg over sine theta. Well, gee, if I factor that mg out as well, I'll get tension equals 1/2 mg times 1 over sine theta. And so that's why each string gets half the weight force. You can also see that this equation still does hold up. It does produce the equation that I produced before. Now let's go to that system I said was going to be a little special. Here's the thing about these equations. They only work when your tensions are the hypotenuses of a triangle. As I proved before, tension 1 is not a hypotenuse. Or is it? I'm going to employ what's called a degenerate triangle. Now, I actually had to Google that term because who would know that off the top of their head? Probably a geometry teacher. But a degenerate triangle is a triangle consisting of 3 collinear points. In other words, I have a straight line, I have 3 dots on that line. Those are my triangle's vertices. So in other words, a degenerate triangle is a triangle with 3 angles, a 0-degree angle, a 0-degree angle, and a 180-degree angle. Now that is very important because now we can define T1 as the hypotenuse of said degenerate triangle. So let's solve for tension 2. We said that tension 2 is equal to mg over sine theta. So tension 2 equals mg over the cosine of the adjacent angle, theta, times the tangent of the opposite angle, which we've already said is 180 degrees, plus the sine of the adjacent angle, theta. Now here's the thing. Tangent of 180 is equal to 0. So that whole first term cancels out, and we get T2 equals mg over sine theta. Oh, look at that. That's exactly what we said before. Well, let's do it for T1 as well. If we're defining T1 as the hypotenuse, then we get T1 equals mg over the adjacent angle, well, cosine of the adjacent angle, 180 times tangent of the opposite angle, theta, plus the sine of 180, because 180 is our adjacent angle. Cosine of 180, well, that simplifies to 1. So I was wrong. I goofed up. Cosine of 180 is actually -1, not +1, but this does still work. It's just a little more complicated and mind-bending. If you take a look at this picture, I basically expanded the degenerate triangle to show that it is in fact a reflection of the actual triangle, meaning that all of its components are negative when compared. This works because we already proved that T1 is just the horizontal component of T2. So the equation is actually mg over negative cosine of 180, tan theta, minus sine of 180. The -1 and the negative sign then just cancel out, and sine of 180 is still 0, which then makes it ng over tan theta. So there's the editor's note. So we get T1 equals mg over tan theta. Oh, look at that. That's exactly what we said it was before as well. So you can see these equations do hold up. It just depends on how you define your tensions. It's all about perspective.